Welcome back to the deep dive. We're closing the loop today. We're at the finale of a mathematical journey that's taken us all the way through this abstract world of nodes and edges.
It really feels like we're bringing it all home now.
Exactly. And if the last few deep dives were about, defining the rules of connection, today is all about defining the limits of connection. We're finally connecting geometry, the world of drawing, of visual constraints, with combinatorics.
Which is the world of counting, conflict, and resource allocation.
That's the bridge?
That is the essential bridge we're crossing. This is where all those theoretical tools we've been building suddenly get a sharp practical focus. We're looking at fundamental constraints.
Like what?
Well, specifically, how much can you connect before the structure just breaks down, before lines have to cross? And then what is the absolute minimum resource, you can think of it as color, that you need to manage all those connections without any conflicts?
Okay, let's really set the scene here. Our mission today is to define the limits of structure, but specifically in two-dimensional space. I think it's something we forget, that physical space itself imposes these deep mathematical boundaries.
It does. We're showing how the act of just drawing on a flat surface, something that sounds so simple, actually dictates these profound truths about what's computationally possible or what's structurally stable versus what is just, a tangled mess.
And this isn't just about doodling on paper. This is deeply relevant to the technology that's probably in your pocket right now. I mean, think about designing a circuit board, a computer chip. In a modern device, you could have millions of connections trying to link up these microscopic components. And if two of those conductive traces cross on the same layer, what happens?
You get a short circuit, it's a catastrophic failure, a device just stops working, it might even burn out.
So every single successful electronic device that relies on these 2D wiring layers, which is almost all of them, has to solve this problem. They have to arrange everything perfectly with zero crossings.
And the moment you start talking about avoiding crossing lines in a dense network, well, you are talking about the core concept for today. You're talking about planarity.
Right, so understanding these geometric laws is the firewall between a working piece of technology and, well, a piece of scrap metal.
It's applied mathematics at its most critical, truly.
Okay, so let's start there with the term itself. Planar graphs. The name kind of gives it away, right? Whether you say planar or the German term Plättbar, it implies flatness.
It does. A planar graph is defined by one single absolute rule. You have to be able to draw it on a flat surface, a piece of paper, a circuit board, a whiteboard, in such a way that no two edges intersect each other.
And the lines themselves can be curvy.
Oh, absolutely. They can be curved, they can be bent, wiggly, that flexibility is totally allowed. But they cannot, under any circumstance, cross over one another.
This isn't just a suggestion, it's a structural demand. I mean, in high-density wiring, designers go to enormous lengths to make sure a layer is planar. If the graph that models their connections is mathematically planar, then great, the design is solvable.
But if it's not?
If it's not, they have to add another physical layer, an expensive one. They're literally adding a third dimension just to untangle the mess they couldn't solve in two.
That's right. For most of our journey in graph theory, we've been drawing graphs any way we like, just haphazardly, which is fine for abstract stuff. But now, the geometry matters. We have to respect the limitations of the 2D plane.
Before we get to the hard constraints, our source touches on this idea of a minor. It sounds a bit technical, but it seems really crucial for understanding the structural purity of a graph.
It is. A minor is just a derived smaller graph. You make one by doing one of two very simple things. Either you just delete an edge, just get rid of it,
Okay.
or you do something called contraction.
What does contraction look like in practice?
Okay, so imagine you have two nodes, and they're connected by a single edge. When you contract that edge, you're basically collapsing it. You merge those two original endpoints into one brand new node.
And what happens to all the other connections?
All the other edges that used to go to either of the original nodes now just attach themselves to this new single merged node.
So you're simplifying the graph, sometimes dramatically, I'd imagine.
Precisely.
Yeah.
And here's the key insight. Planarity is an inherited property. If the big original graph you started with is planar, if you can draw it without crossings, then any minor you make from it, no matter how much you delete or contract, will also be planar.
So the structural integrity, the possibility of a clean 2D layout is preserved all the way down.
Exactly. It's like saying if a balloon is intact, you can shrink it and it will still be a functional, intact balloon. The fundamental character remains.
Okay, so when we draw one of these graphs on a plane, we're basically carving up the surface. And this leads to the three fundamental components we need for the main event, V, E, and F.
Vertices, edges, and faces.
Vertices and edges, we know those, the nodes and the connections.
Hmm.
But the faces, F, those are the regions that the drawing cuts the plane into. How do we make sure we count those correctly?
The count has to be really rigorous. A face is any contiguous region that's bounded by edges. And this is the one detail everyone forgets at first. There's one absolutely critical piece.
Let me guess. The outside.
The outside. You must include the vast, unbounded region that surrounds the entire graph. That counts as one of the faces.
Right, so that whole infinite area is F1.
That's right, it's F1. And then all the little regions trapped inside cycles are F2, F3, and so on. If you forget to count that external face, the mathematical magic we're about to reveal it completely breaks. You have to account for the whole surface.
Which brings us to, I think it's fair to call it, one of the most remarkable theorems in all of mathematics. A rule of connection that feels as constant as gravity. Euler's polyhedron formula.
It is pure magic, absolute magic. Leonhard Euler first found this for 3D shapes, for polyhedra, but it translates perfectly to connected planar graphs. It's the unifying principle of flat geometry.
And it says that the relationship between the faces F, the edges E, and the vertices V for any connected planar graph is constant.
It's always constant.
And that constant is simply 2.
Simply 2. F minus E plus V equals 2. I mean, just stop and think about the implication of that for a second. You can take any connected graph that you can draw without crossings. Let's say a map of your city's subway lines.
Okay.
And you count the stations, that's V. You count the tracks between them, that's E. And you count the regions they enclose, that's F, including the outside world. And no matter how convoluted that map is, no matter how much you stretch it or squish it, that calculation will always, always give you the number 2.
It's an invariant, a law of nature for how things connect on a flat surface. It's telling us these three properties aren't independent at all. They're fundamentally linked by the geometry itself.
And the proof for this beautiful theorem, it has this incredible economy of effort. Our source lays it out with the logic of induction over the number of faces. It's a story of simplification.
And induction always starts with the absolute simplest case possible.
Correct. We start with the base case. What if F equals 1? If a connected planar graph only has one face, what does that mean?
It just means the outside region. There are no loops, no internal boundaries.
And what do we call a connected graph with no cycles?
That's the definition of a tree.
Exactly. And for any tree, we already know a definitive rule. The number of edges, E, is always exactly 1 less than the number of vertices, V. So E equals V minus 1.
Yeah, so let's plug that into Euler's formula. We have F minus E plus V.
Right. So we substitute what we know. F is 1, E is V minus 1, and V is V. So you get 1 minus, in parentheses, V minus 1 plus V.
Okay, so the minus V and the plus V cancel each other out. And you're left with 1 minus negative 1.
Yeah.
Which is 1 plus 1. It's 2.
It's 2. The base case holds. The formula works for the simplest possible connected planar structure.
Perfect. Now for the intellectual leap, the inductive step. We have to prove that if the formula works for a graph with, say, k faces, it also has to work for a graph with k plus 1 faces.
Right. So if our graph has more than one face, it must have at least one internal cycle, a closed loop. Otherwise, you couldn't have those internal face boundaries.
Makes sense.
So we find one of those cycles and we just pick one edge in it. Let's call an edge E.
And the action we take is just remove it.
Just remove you. And removing it has this very specific dual effect. First, obviously, the number of edges, E, goes down by 1.
Right.
But second, because that edge was the border separating two different faces, when you remove it, those two faces merge into one bigger face.
So the number of faces, F, also goes down by 1, but the vertices, V, stay the same.
Exactly. So we started by assuming the formula held true. F minus E plus V equals 2. Now we apply our changes. We have F minus 1 minus E minus 1 plus V.
And if you distribute the negative sign, you get F minus 1 minus E plus 1 plus V.
The minus 1 and the plus 1 cancel.
They cancel each other out. So the change we made perfectly balanced itself. The formula is still F minus E plus V, which we assumed was 2.
The equality is preserved. And you can just keep doing that, keep removing cycle edges one by one until you've reduced the whole graph back to its tree core where we already know it works. It shows that this constancy is a universal feature.
And that's where the magic really sinks in for me. This simple geometric constant forces these massive structural limitations on us. If F minus E plus V must equal 2, it means you can't just keep adding connections forever and ever. Planar graphs cannot be too dense.
That is the single most important practical implication. The 2D surface just runs out of room, and it runs out of room fast. And this leads to two consequences that are absolutely vital.
Okay, the first one is the degree constraint. This seems really powerful.
It's huge. It states that every planar graph with at least 3 nodes must have at least one node whose degree is at most 5. So degree less than or equal to 5. You cannot build a planar graph that avoids this.
So in real-world terms, you can't design a circuit board where every single component connects to 6 or 7 or 8 other components, all in one layer, without crossings. The geometry just says no.
It absolutely forbids it. Somewhere in that complex structure, there's always a weak link, a relatively simple component with 5 or fewer connections.
If you try to force it, if you try to make every node connect to 6 or more neighbors,
the density immediately pushes you over the edge. Crossings become inevitable, and this property, this guaranteed existence of a low-degree node, is the conceptual lever we are going to use later to solve coloring problems.
Okay, and the second consequence gives us a hard number, a quantifiable limit. The edge constraint.
This is the definitive boundary. For any planar graph with V vertices, where V is at least 3, the absolute maximum number of edges it can have is 3V minus 6.
3V minus 6. Let's just pause on what that number means. If I have a network with, say, 50 nodes, I can just do the math. 3 times 50 is 150, minus 6 is 144.
Yep.
So I know, without even trying to draw it, that if I try to make 145 connections among those 50 nodes, I am mathematically guaranteed to have crossing lines.
It's a mathematically proven short circuit. You've exceeded the capacity of the plane. And this boundary is derived directly from Euler's formula and the fact that the densest possible planar graph is one where every face is a triangle. The moment you go past 3V minus 6, you have structurally guaranteed that it cannot be planar.
So we know the hard limit where planarity breaks. But what about the patterns that cause it to break? We need the answer to the core question. What are the forbidden structures?
And that is answered by what I think is one of the most elegant theorems in all of graph theory. Grotowski's theorem.
Okay.
It gives you the necessary and sufficient condition for planarity. It's the final word.
So what does it state?
It says that a graph is planar if and only if it does not contain two very specific graphs as a minor. Remember minors?
The simplified versions?
Exactly. So if the structural essence of either of these two offenders is hidden anywhere inside your big, complicated graph, then the whole thing is non-planar. Game over.
These are the two fundamental ways to break the 2D constraint. Let's look at the first one, K5.
K5. This is the complete graph with 5 vertices. And complete means every single one of those 5 nodes is connected to every other node.
So 5 nodes, 10 total edges.
Right. And you can feel this one intuitively. If you try to place 5 dots on a piece of paper and draw all 10 lines between them, you will inevitably have to cross a line. There's no way around it.
You can almost feel the density limit being broken. 5 nodes feel so small, but those internal connections just overwhelm the 2D space.
The geometry just demands too much traffic through that central region. K5 represents the structural limit of pure density.
Okay, and the second forbidden pattern is K33. This one feels like it models a different kind of conflict.
It does. K33 is the complete bipartite graph. You might know it from the classic 3 utilities puzzle.
Oh, right. 3 houses and 3 utilities. Water, gas, electricity.
That's the one. You have 2 sets of nodes. 3 nodes in set A, the houses. 3 nodes in set B, the utilities. And every node in set A has to connect to every node in set B.
But crucially, no connections within a set. So no house connects to another house.
Correct. So you have 9 total connections. And the puzzle is, can you draw those 9 lines without any of them crossing? And the answer is no. The bipartite structure forces the connections to bridge that gap in a way that just creates unavoidable conflict.
So Kuratowski's theorem is like the ultimate diagnostic tool. If you're designing some massive, complex network, you don't have to try millions of different drawings.
You don't. You just have to check if that complexity, once you simplify it down using minors, contains the structural skeleton of either 5 nodes all talking to each other, K5.
Or that 3-on-3 bipartite conflict, K33.
If it does, planarity is impossible. They're the twin scapegoats of 2D geometry. Find them, and your case is closed.
So now we take this conceptual understanding of geometric limits, of this non-crossing rule, and we pivot. We use that knowledge to move into the world of counting, of efficiency, of resource allocation. We're going for the geometry of drawing to the combinatorics of, what's the German?
Verknüpften Verbindungen. Node coloring.
Node coloring.
Node coloring, right.
And we shift our focus from spatial limits to conflict management. The colors are just abstract tools, really. But in the real world, they represent resources that can't be shared at the same time.
What's amazing is how universal these coloring problems are. This is what takes graph theory out of the pure math department and puts it right into, like, logistical management.
The absolute classic example is scheduling. Imagine you're making a school timetable. Every class is a node.
Okay.
If two classes require the same limited resource, say they're both taught by the same teacher, or they both need the one chemistry lab, we draw an edge between them. That edge means conflict.
And the colors are the time slots in the day. Exactly. If we give the same color, the same time slot, to two nodes connected by an edge, we have a clash. Two classes, one lab, it doesn't work. The goal is to find the minimum number of colors, the fewest time slots, needed to schedule everything without a single conflict.
It's all about maximizing resource use. Another great example is in telecommunications, right? Assigning frequencies.
Cellular towers, perfect example. Each tower is a node. If two towers are close enough that their broadcast signals would interfere with each other, we connect them with an edge.
They can't use the same frequency.
They can't, so the colors represent the available frequency bands. The problem is, how do you use the minimum number of frequencies to cover your entire network without any interference, saving that precious, expensive bandwidth?
So let's define the terms properly here. What exactly is a K coloring?
A K-coloring is simply an assignment of distinct colors to all the nodes in your graph while following the one golden rule of coloring. No two nodes connected by an edge are allowed to have the same color.
So it's a successful, conflict-free allocation using K resources.
That's it. And the real challenge, the optimization puzzle, is to find the smallest possible number K that works for the whole graph. And that smallest number has a special name. It's called the chromatic number, written as chi of G.
The chromatic number. So that's like the inherent difficulty rating of the graph's resource needs.
You can think of it that way, yes. A high chromatic number means the network is complex, tightly interconnected, and needs a lot of different resources to manage. A low one means it's relatively simple to untangle.
Okay, so let's talk about the theoretical boundaries here. The bounds and constraints on that chromatic number. How can we get a quick estimate of what a graph might need?
We can bracket it. We can find an upper limit and a lower limit. The upper bound is surprisingly simple. It's determined by the single most connected node in the entire network. We call its number of connections the maximum degree, or delta. Delta.
The intuition here seems to be that if I'm a node that needs a color, the absolute worst case scenario is that all of my neighbors have already been colored, and they all took a unique color.
That's it, precisely. So if the busiest node in your graph, the one with the maximum degree delta, has, say, 10 neighbors, then we are absolutely guaranteed that 11 colors will be enough for the whole graph.
So delta plus 1. Delta plus delta 1.
Yes, delta plus 11. Because even that most connected node only has 10 neighbors blocking colors. The 11th color is guaranteed to be available for it. It's a safe bet for planners, even if it's not always the most efficient number.
That's a nice bit of security. Now, what about the other end? The lower bound, our source says that's defined by the largest clique.
A clique, right. A clique is a complete subgraph. It's a little pocket within your bigger graph where everybody is connected to everybody else.
So imagine 5 university courses that all need the one single super specialized piece of lab equipment. They are all mutually in conflict.
That's a perfect 5 clique. And since every node in that clique is connected to every other node in it, they all must have a unique color. They can't share a time slot. So if the size of your largest clique is omega G, then you need at least that many colors just to solve that one small, dense part of the graph. So these two bounds give us a window. The true chromatic number, the perfect minimum, has to be somewhere between the size of its biggest internal gang, the clique, and one more than the connections of its most popular individual, the max degree.
That's a great way to put it. And the proof that delta plus 1 colors is always enough is actually a very clean, constructive proof. It's similar in style to the one for Euler's formula.
It's another one based on simplifying and then reinserting.
That's right. You want to prove that delta plus delta 1 colors will always work. So you take any graph G, you just pick one node and pull it out for a moment. You then assume, this is the induction hypothesis, that the smaller graph left behind can be colored with your delta plus delta 1 colors.
Okay, we assume the smaller version works. Now, we put U back in. Now, U has some number of neighbors, D, and D, by definition, can't be more than the maximum degree, delta. So its neighbors are using, at most, delta different colors among them.
But we have delta plus DeLong colors available in our palette.
So there must be at least one color left over that none of its neighbors are using. We just assign that free color to it. And since we can always find a color for that final node, it proves that delta plus DeLong colors are always sufficient for the whole graph.
I like that because it gives you an immediate algorithm, a recipe for how to actually color something.
Yeah.
And this is what leads us to the critical link between the geometry we discussed earlier and this coloring problem,
It leads us directly to the six-color theorem.
which states that 6 colors are sufficient to color any planar graph. Any of them. Why 6? That seems so specific.
It's because of the geometric constraint we proved with Euler's formula. Remember what we established back in section 2? Every single planar graph must have at least one node with a degree of 5 or less.
The weak link. You can't escape it.
You can't escape it. It's a structural necessity. So that low-degree node is the key that guarantees us a slot in the schedule. If we just apply that general delta plus Alardo coloring rule to the specific reality of planar graphs.
Well, the worst case node we can always find has a degree of 5.
At most 5. So 5 plus 1 is 6. 6 colors must be enough.
Let's walk through that constructive proof, that algorithm for the 6-color theorem, because this is a perfect example of how a structural property leads directly to an efficient solution.
Okay, so we use induction, and we lean on that guaranteed low-degree node. Step 1 is the base case. If your graph is tiny, say 6 nodes or fewer, then of course 6 colors are enough. That's trivial.
Right. Step 2. For any larger planar graph, we know for a fact we can find at least one node, let's call it U again, where the degree of U is less than or equal to 5.
We find our weak link. That's our pivot point.
Step 3.
We remove it, just like before. The graph that's left is smaller, and it's still planar, so by our induction hypothesis, we assume we can successfully color it using our 6 colors.
And now, for the final step, step 4. We put it back in.
We reinsert of S. And because S has at most 5 neighbors, those 5 neighbors can only be using at most 5 of our 6 available colors.
Which means one color is guaranteed to be free for us.
Guaranteed. We color up with that available color, and the proof is complete. It's a beautiful piece of logic.
The elegance is that Euler's formula, which is a pure geometry thing, created the structural loophole, that low-degree node, which in turn provides the combinatorial solution. The drawing rule makes the scheduling problem fundamentally easier.
It does. Now, the source does mention that you can actually tighten this bound to 5 colors.
Right, using something called a Kempe chain argument.
Yes, and I want to stress, the 6-color proof is beautifully straightforward and constructive. The 5-color proof is, well, it's a lot more complicated. It relies on a clever trick.
What's the trick?
The idea is that you get to that last step, you put node U back in, and what if you're unlucky? What if its 5 neighbors happen to be using 5 unique colors? Then you have to do more work. You have to analyze the color patterns extending out from those neighbors. You look for an alternating path of 2 colors, a Kempe chain, and if you can flip the colors along that path, you can free up a color for it.
So just reducing the resource need by 1, from 6 down to 5, introduces this huge leap in the complexity of the proof.
An exponential leap. It forces you to look at the global consequences of your local coloring choices. And that brings us to the ultimate boundary, the theorem that basically defined a new era in mathematics, the 4-color theorem.
The famous map coloring problem. This theorem states that 4 colors are all you ever need to color any possible planar graph, any map you can draw on a globe or a flat sheet of paper.
4 colors is the absolute minimum, and this simple-sounding statement stood as this enormous, unsolved intellectual challenge for more than a century. The jump from proving 6 colors is easy, or even that 5 colors is possible with difficulty, to proving that 4 colors is the absolute minimum. That required what the source calls heavy artillery.
Why was it so impossibly hard? What's so special about the gap between 5 and 4?
The jump from 5 to 4 involves this deep, irreducible complexity. The 6-color and 5-color proofs were constructive. They gave you an algorithm. The 4-color proof, which was finally nailed down by Appel and Haken in 1976, was non-constructive. And critically, it was the first major mathematical theorem to rely fundamentally on computer verification.
The story of this proof is just a sensation. They didn't come up with a single elegant argument. They proved it by reducing the infinite number of possible maps to a large but finite set of difficult configurations.
An unavoidable set, they called it. And that set contained 1,476 distinct configurations. They proved that every possible planar graph must contain one of these 1,476 configurations. And then they proved one by one that each of those configurations could be reduced, that it could be colored with 4 colors.
And a single human being could not possibly check all 1,476 cases and all the millions of calculations without making a mistake.
No, it took hundreds of hours of computer time running these verification algorithms, and it forced the mathematical community to grapple with this huge philosophical question. Is a proof really a proof if no single human mind can verify every single step? It was a tectonic shift. It showed us that for some problems, the complexity is just beyond human scale. We need machines.
So the six-color proof is this elegant piece of human deduction. The four-color proof is a brute force, exhaustive demonstration of truth, requiring the computational power of entire machine age.
Exactly. The chasm between easy to prove it's possible and proving the absolute minimum can hide an immense, unexpected depth of complexity.
What an incredible place to wrap up our exploration. Let's trace that thread one last time for you. We started with a purely geometrical problem. How do you draw things without crossing lines? We defined planarity.
And that structural definition led us straight to Euler's polyhedron formula, F minus E plus V equals 2, which revealed this profound, constant law of nature for flat geometry.
We then used that law to quantify the limits of 2D space. It told us that density is limited by that 3v minus 6 edge constraint, and that we're always guaranteed to find a simple, low-degree node.
And we identified the 2 fundamental spoilers, the forbidden patterns that break planarity, the pure density of K5, and the bipartite conflict of K33.
And finally, we took all of those geometric insights and we applied them to solve these complex logistical problems using coloring. We showed how planarity makes the six-color theorem almost trivial to prove.
And we wrapped with the story of the 4-color theorem, a monumental achievement that forced us to understand the limits of our own verification and the staggering complexity hidden in just reducing a resource problem by one single unit.
So my final thought for you is this. When you look at your city map or a subway diagram, or even just the layout of apps on your phone, remember that the simplicity and the efficiency you see there are governed by the elegant necessity of Euler's formula and the structural limits of Kuratowski's theorem.
And the fact that the simple, human-provable solution gives you 6 colors, while the absolute minimal solution of 4 colors requires immense computational power. That tells us that we should never confuse what is simple to state with what is simple to prove. Even in these seemingly basic geometric problems, there is always a deeper, machine-level complexity just waiting to be uncovered.
It reminds you that the pursuit of absolute efficiency, that quest for the minimum possible resource, is often where the real mathematical monsters lie. Thank you for joining us on this deep dive into the hidden geometry of connections. Now go out there and look for the graphs. You'll start seeing the structure and the chaos.
Until next time.